Hello, everyone. Anybody have any questions while we're waiting for everybody to come in?
Nope.
Okay, your practice tests for the midterm will be up today. I think I might have already made them up for this class, but I'm not positive. But there will be the one that you're supposed to take multiple times. That's the one that doesn't require respondents, but I do want you to take the respondents one time. And that one, you actually get to see the answers to. So whatever, you should work them out and try to get the right answer. And it will not only tell you whether you're right or wrong, it's going to tell you the right answer on that. So make sure you do that one time. And then from there on out, of course, you just do the other one as many times as you can, because the more times you do the practice test, the more likely you are to see up to 80% of the points on the test, or at least 80%, I should say.
Can we redo the respondus one as much as we want to?
No, just that you just get one poke at that.
Okay.
So, anybody else have any questions? All right, well, it's only 11 students in here, but there's normally more than that. So I guess I'll go ahead and get started either way. We're going to go ahead and finish up chapter 7 today, and I'm probably going to start into chapter 8 as well. So last time we had learned some things. We learned the work energy theorem. We also learned, well, I'm pretty sure we learned the work energy theorem. We also learned about the different ways you can calculate work. So, and actually I'm checking that right now just to make sure. No, I did not show you the work energy theorem. So that's on the agenda of the day. But I made a little boo-boo. I mentioned it in the notes. You probably even saw it. And if you downloaded the notes for the class, you saw that I've actually made the correction. So I thought I'd go over that today just to show you what I sort of messed up on. So the formulas we had for work, I'm gonna go ahead and turn on the document cam. But the formulas we had for work were, in the case where the magnitude of the force didn't change anywhere along the path that the object was being pushed or whatever, or at least that and the orientation didn't change, we could use work is just equal to F dot D. However, the more general expression, in case any of that changes, was work is equal to the integral of F dot DL. And I made a big deal about telling you how that's a line integral. And I tried to show you a case where you could actually see that the line integral, if you didn't follow directions, you get the wrong answer. So let me show you that again. So what we're going to do is we're going to imagine a spring attached to a wall over a floor, like so. I'll have the mass, say, right here. And I'm going to draw my y-axis right here so that the origin is right here. And the x-axis will be right there. My spring will look like this. Okay, but what I'm going to do is I'm going to give it a little push so that now the spring, applying this force F, which has to be strong enough to overcome the spring, so its magnitude has to be equal to K times X. And last time, this is where I made the boo-boo. I forgot that I'm using just X there, not the absolute value of X. That's not strictly what I was forgetting, but by using K times X, this is for only X equals 0 and beyond, so X is negative. So I've already included the direction by including the X there. In the other chance when I did it, I put a negative KX in there just instinctively because I knew it was pointing to the left, but I should have paid closer attention. So ultimately what I do is I say I move the spring or the mass so far that it went to this position, negative X2. And then of course the spring is like that now. So I wanted to calculate that work two different ways and show you that it actually is positive, because whenever you have a force applied to an object and that force has at least one component that's parallel to the motion that results, then that work should be positive. And remember, in the last class, I ended up getting a negative, so that was a problem. But the rule is, remember, when you use this, you have to use either this or this to indicate direction. One must indicate integration direction. The other just goes in positive coordinate direction. So that's the big rule I was trying to show you. So keep that in mind when you're doing a line integral, is you either have to let the DL show which way you're going or let the range of integration show which way you're going. So in this case, I'm going to do let DL change it. Okay, so I'm going to say work is equal to the integral of kx I hat dotted with, I'm letting the DL show it. So I'm going to put a negative dx I hat. That negative indicates that I'm going from right to left. Well, that means this other one has to be put in the increasing coordinate direction. And that, of course, is negative x2 to 0. That's not the way we're going, notice. Okay, that's actually the opposite way we're going, but it's in the positive coordinate direction. In other words, this number down here is smaller than that number. So that's why this works out. And I'll get negative k integral negative x2 to 0 of x dx. And of course, I hat dot I hat is just 1. I'll use the linearity there to do that. So this is going to come out to be negative 1/2 k x squared from negative x2 to 0. And that, of course, is equal to negative 1/2 k times 0 squared minus negative x2 squared, which I think you can see is not the minus on the x2 that makes it become positive. It's the fact that it's the second answer. So the answer I get is, in fact, 1/2 k x2 squared, which is a positive quantity. And that's exactly what we expect the work to do, since it was, in fact, going applying a force in the same direction of the motion. I didn't like how ugly that 2 became, but it's evidently just getting uglier, so I'll leave it be. All right. So that's how you do it when you let the DL show you. Now let's let the range show you. So now I'm going to say work is equal to the integral. Now I'm going to go from 0 to negative x2. So that's doing my direction. So negative 0 to negative x2, it's still kx I hat, because that takes into account the direction of the force. And then this one has to point in the positive coordinate direction, so that's dx I hat. So I think you can see I'm going to get 1/2 k x squared, and this is from 0 to negative x2. Well, that's going to be 1/2 k times negative x2 squared minus 0 squared, which equals 1/2 k x2 squared again. Okay, so that's the critical point. I just wanted to make sure you guys got it. That's the nature of a line integral. You'll learn different ways to do it. Like if you look in your near end chapters of your calculus textbook, you'll see that they do line integrals and surface integrals, but they do them in a lot different way. They usually use parametric equations to define the curve, and then they take the differential of that parametric equation and some stuff like that. It's exactly equivalent, but again, it's just a different way that we don't do here in physics usually. We can, sometimes we're forced to if we're a little sketchy on on what steps they're taking. So now what I'm going to do is show you another example. We've given you an example where the force changes as a function of position. So I'm going to show you yet another example where the force is changing as a function of position, and it's going to give me a neat little result. Specifically, it's going to give me a result that happens to be relativistically correct, even though it's not done with relativity. So in this example, I'm going to try to calculate a formula for the work done in moving an object of mass m, say, from the surface of the Earth The radius for the surface of the Earth is r with a little circle and a plus around it. I'm going to move it from the surface of the Earth out to infinity. In other words, I'm going to escape gravity. This is basically your escape energy. What energy is required to escape the Earth? Okay. I want to know what energy is required, or let's say what work is required to escape Earth's gravity. That's part A. And then part B, assuming that work, I don't know I'll put it, you don't need to know work. Assuming that work is provided by the initial kinetic energy of the object and that its speed was c equals 299,792,458 meters per second, which is the speed of light. What, in other words, we're pretending like the Earth is a black hole, like we're requiring it to have such a strong gravitational field that only something traveling at the speed of the light can actually escape it. So what would Earth's radius be? Now, this is basically the black hole radius or the Schwarzschild radius for an object the size of the mass of the Earth. And it turns out to be exactly the right formula. That's why I like it. The big thing is, and this comes from the work energy theorem, so I'm going to introduce that in a second, but there's a concept called kinetic energy, and we label kinetic energy either K or KE. And it's basically the object's 1/2 of the object's mass times the square of its velocity. So that's what kinetic energy is. So first off, I want to calculate that work as asked for in part A. So work is equal to the integral of F dot dl. Well, we know from chapter 6 what the force is. The force is due to gravity. So I'm going to say it's equal to G, the gravitational constant, times M, the mass of the object, times M plus, which is the mass of the Earth, over R squared. And that force, I'm going to have to push radially outward. So it's going to act in the radial direction. And then I got to dot that with DL. I'm going to use the DL to indicate my direction of travel. So I'm going to say that is dr r hat. Again, this r hat is just a special vector that we use for spherical coordinates, but it's 1 unit long and it points radially outward from the origin. Okay, you could actually work it out in terms of I hat, J hat, K hat, and that comes in handy like in a statics and dynamic class. That's a good thing to do. I do it for you. I think I've even done it on my YouTube channel. Now, with that in mind, now I'm supposed to go in the positive coordinate direction for this because I chose that to indicate my direction. Well, it happens to be that I'm going both of them the same way, so it doesn't matter. So I'm going to go from the radius of the Earth to infinity. And you may not have covered yet how to deal with the range of integration that's infinity, but I'll show you that too. So now that we do that, I'm going to pull out the G, the M, and the M plus. out front because they're definitely constants. The r hat dot r hat, that can be that's a linear operator, so I can pull all that junk out in front. And I'm going to say from r plus to infinity again. And now I get dr over r squared, which is r to the -2 is what you're integrating. R hat dot r hat, because they're both unit vectors, is 1 times 1 times the cosine of 0, which is 1. So that whole thing's 1. Now all I got to do is realize that the integral of r to the -2 is negative r to the -1. So now I'm going to say negative g m plus over r like that. Now I got to evaluate the integral from r plus, which is the Earth's radius, to infinity. The way I do that is I'm going to pull this all out in front and say negative g m's plus times the limit. This is the way you handle a infinite range. The limit as r approaches infinity of 1 over r minus 1 over this one, which is r plus. Okay. So it's clear that the limit of 1 over r as r approaches infinity. I think everybody knows that's 0. So that gets rid of the negative sign, and we ultimately just left with a neat new formula, g m over r that. Okay. So that's the work required to escape Earth's gravitational well. That's the answer to part A. Any questions on that? Now let's say that all of this work is just going to come from basically losing the kinetic energy of a projectile. In other words, we're going to fire a rocket that instantaneously at the Earth's surface is going to be traveling at the speed of light. And it has a mass m. And we're going to say that's just enough energy so that it slows down, 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 boom, comes 0, just as the spacecraft gets to infinity. If that's the case, then we can say 1/2 the mass of the spacecraft times c squared is equal to g times the mass of the spacecraft times the mass of the Earth divided by the radius of the Earth, like so. Now you can see the little m's cancel out, and in fact we can solve for the radius and we get exactly the right formula. The radius, just dropping the pluses for a second just to show the general result, the radius is 2gm over c squared. That's exactly the Schwarzschild radius. Okay. In other words, when you work out general relativity and you choose a bunch of symmetries, you can get basically what we call a metric for the space-time, and it's called the Schwarzschild metric. And basically the point of no return is the Schwarzschild radius. So once you come within that distance of a black hole, you're not ever going to get back out again. So what we're asked here to do is calculate what this radius of the Earth would be as a black hole. So I'll write that as our Earth black hole, and that's just 6.67. Yes.
I have a question.
Yes.
When you're saying r plus, are you saying the radius of Earth like current, or are you talking about any input radius?
Well, you can look up in tables and they'll have different symbols for different planets, and you could put any symbol there and there and you'd still get the right answer for those particular planets. But what I'm saying is this case, I'm going to solve for the Earth's radius if it were a black hole. In this case up here, I actually would have to use the Earth's mass and the Earth's radius as they really are.
Okay, so it's proportional to the planet.
Exactly. Yeah, whichever planet or sun or whatever you're using, you put that mass and radius in there, and that'll give you the work done to escape it. And you can, instead of using c, you can actually use just 1/2 mv squared like this, and then that would give you the escape velocity. So if you chose to do 1/2 mv squared is equal to g m times the mass of whatever body over the radius of whatever body, then you get the escape velocity. So you can just write it as ESC, escape velocity. And that, again, the masses cancel out, but that's nice too, because if you want to know what the escape velocity of the Earth is, now you just solve for the escape. Now the units here are newtons, meters squared per kilogram squared. And then I forgot the 2, so I'll put that there now. And the mass of the Earth is 5.98 times 10 to the 28th kilograms. And then divided by 299,792,458. And you don't have to actually write all that down. I don't even know why I did it.
Is the mass of the Earth to the 28th or the 24th?
24th, thank you. Nice catch. That would have screwed everything up. Yeah, 10 to the 24th. So when I do this calculation, I get 8.8759 times 10 to the -3 meters, which really is about 8.88 millimeters. So if you wanted to make the Earth as powerful as a black hole, the Earth would have to have a diameter of about 1.6 centimeters. That's the diameter now. So just to give you a reference on that, the radius would be about that, but the diameter would be about that. So from 0 to the a little bit past the mark after the half. So about that big is how big Earth would be if it were to be a black hole.
8.8 millimeters.
Yes, 8 millimeters. These individual marks are also millimeters. They're tenths of a centimeter, but that means the same thing as a millimeter. So yeah, we're looking at roughly 9 for the radius. Oh, I said one. I meant 1.8, not 1.6. Excuse me. So it's right about there for the radius, which would be right about there. Sorry, for the diameter. So that's about, I don't know, about as wide as my thumb, or at least a little bit wider than my thumbnail. So again, that's a neat little thing to do. And like I said, you can also use it to find the escape velocity for a planet. So that's a whole nother neat thing you can do. So V escape would be the square root of 2gm over r. So that's a neat new expression that I found as well. Not necessary for this problem, wasn't asked for, but it is kind of neat that you can do it now. Any questions on that? All right, so now all of a sudden you have a sense of why a black hole is not really necessarily anything special. In fact, it turned out to be exactly what you'd expect. Anybody thought if you made a thing small enough, it might get, the force of gravity might get so strong that nothing could escape it. And in fact, that is the case, but obviously the Earth would have to be super small. If you want to do that for the sun, you'd see the sun could be a little bit bigger. Well, actually, it's a lot bigger, about 10 to the, about 1 million times bigger. So it's actually more like 500,000 times bigger. So it's at least on the order of meters. Now, beyond that, I need to do something. I need to do a derivation of the work energy theorem. And that's what we're going to do now. So work energy theorem. So one of the common uses of this is you could use it to figure out, for instance, when you measure a length of a skid mark, say at a wreck or something, you can use that to determine the velocity of the car or the speed of the car when it started hitting the brakes. And, you know, obviously that could be used in a court of law, that sort of thing. But that's the work energy theorem. And let me show you how it is. We know that work is equal to the integral of F dot dl. And we also know that the summation of the forces, which is also called F net, is equal to m times dv dt. Okay. So if we wanted to know what the net work was, that would be the integral of F net dotted with dl. So we could say, oh, well, I know that F net is in fact the integral, or the integral of F net dot dl would be in fact M dv dt dotted with dl. Now, and dl is a vector too. Now we can switch roles between dl and dv and say the integral of M dl dt dotted with v, and dl dt is obviously going to be parallel with v because dl dt is v. So the dot product just becomes plain multiplication. So we get the integral of M v mv dv, yeah, mv dv. Okay, the reason why, of course, is the dl to dt becomes the v. Now you got mv dv, and when we integrate that, we end up getting 1/2 mv squared, and that of course goes from v initial to v final. So what we've learned is that the net work done on any system is equal to 1/2 mv final squared minus 1/2 mv initial squared. And that gave us the idea of defining the quantity kinetic energy as 1/2 mv squared. So we now know the work energy theorem says that the net work done on anything is always equal to the change in kinetic energy of that thing. And remember, the delta symbol always means final minus initial. So that's why it's 1/2 m final squared minus 1/2 mv initial squared. So that's the work energy theorem. Any questions on that?
The units of work are the same as torque in moments, right?
Yes.
Pounds,
Yeah, it's a
pounds
Newton times
feet.
a meter, but we call it a joule when we're dealing with energy.
Okay.
Okay. And remember, the rule of thumb I gave you was 1 joule is about as much energy as it takes to lift a red delicious apple from the floor to a dining room table. So that's a nice little rule of thumb to go by. So let's look at an example. Let's say example 2. What I'd like to know is, what is the work done by a softball pitcher accelerating a softball from 0 to 60? So how much work must a softball pitcher do to bring the velocity of a 190.0 gram ball from 0 miles per hour to 60 miles per hour? So this is a straightforward application of the work energy theorem. So we know that work net is equal to the change in kinetic energy, which equals 1/2 m times v final squared minus v initial squared. Well, 1/2 m would be 1/2 times 0.1900 kilograms. Gotta make sure you use kilograms, times v final. 60 miles per hour is about 26.8 meters per second. Whoa, 26.8 meters per second. So I'm going to square that minus 0 squared. And lo and behold, when we do that, I get 68.23 joules. So it's about equivalent to lifting 68 red delicious apples to the table. And that, seems about right, because red delicious apple is probably comparable in mass to actual red softball. So you can imagine, lifting about 68 of them might be able to bring a ball up 60 miles per hour. And 60 is a good middle of the road pitching speed for a good female softball player. I think Finch was more like in the 70s. and some more recent pictures I've seen go higher than 70. But anyways, that's a good rule of thumb. Any questions
Wait.
on that one?
Where did you get the 26.8?
That's a conversion of 60 miles per hour to meters per second.
Oh,
I've
okay.
used that a few times, so I just figured y'all remembered it. Okay, let's try another example, something else we've also talked about before. And that is how much work is done by, I did dome instead of done, oh well, done by Tesla's Model S plaid motor. Notice I said motor, not engine. Model S plaid motor in reaching 60 miles per hour in 1.98 seconds if the Model S weighs 4,766 pounds, which is approximately 2,250 kilograms. And in part B, how much power? Power is required on average. Oops. Whoop. Okay. So part A, work net is equal to the change in kinetic energy, which is again 1/2 times the mass, that's 2,250 kilograms, times V final, which would be 26.8 meters per second squared. Remember, it did 0 to 60 in 1.98 seconds in that video I shared with you guys, minus 0 seconds or 0 meters per second squared. And when I do this math, what do we get? So I do 0.5 times 2250 times 26.8 squared. And that gives me 808.02 times 10 to the third joules. Okay. Or you could say that's about 808 kilojoules. Now, part B, they want to know the power, the average power, and average power is just work divided by time taken. In other words, generally power is dW dt, but if we just take the amount of work done divided by the total time taken, then we get the average. So this is close enough. I'll say 808.02 times 10 to the third joules divided by 1.98 seconds. So I'm going to take that number and divide it by 1.98, and I'll get 408.09 times 10 to the third watts. Now, Tesla advertises that their Model S has 1,020 horsepower. Okay, let's see how that compares to this. So 408.09 times 10 to the third watts times 1 horsepower is equal to 746 watts. So if I take that number and divide it by 746, then I get about 547.04 horsepower. Okay, so that's kind of neat. They advertise 1020. And in doing that, the average is only about 547, but that's still pretty impressive because remember what's probably going to happen if you did a velocity or a position versus time graph. Let's say X versus T, you'd probably get something really sharp like that and then going off like that over the time interval of about, let's say, 2 seconds. And this part right here is the vast majority of the acceleration. So I would guess, for instance, probably takes, let's just spitball it here. Let's say the total travel time is 2 seconds. I would venture to say that maybe 0.50 seconds, it goes from 0 to 30 miles per hour. And then the remaining 1.5 might be what's required for it to get from 30 to 60. And if you work that out, I bet you'd come closer to getting 10,000 or 1,020 horsepower. So in other words, even just 0 to 60 in 2 seconds, you're probably maxing out its acceleration initially, or maxing out its power initially by maxing out its acceleration in the first maybe 25% of the acceleration. So maybe at 0.5, the slope is 30 miles per hour. Okay, so hopefully that makes some sense to you guys. Any questions on that? All right, another type of problem you can work on this is, like I said earlier, let's say the Tesla, this will be example 4, right? Example 4. Let's say the coefficient of static friction, so mu sub k, is equal to 0.410. And that's basically between the rubber that's on the Tesla's Plaid's tires and the asphalt that we're actually running it on. And let's say the mass of the Tesla is equal to 2,250 kilograms. And let's say mu, I wanted mu kinetic actually to be the smaller one. Mu static is probably 0.410. Let's change this mu kinetic to 0.205. So change that kinetic friction to 0.205. I remember looking up in some tables for engineering, transportation engineering, and I think I saw somewhere between 0.4 and 0.5 for the static coefficient of friction of rubber on asphalt, which is sort of the best case scenario. So let's say the kinetic friction is that, and compute how long of a skid mark is made by slamming on the brakes at 60 miles per hour. Okay, so we're pretending we're not using any of those fancy technologies like anti-skid brakes and that sort of thing, which, by the way, they really do work. And in fact, I've caught myself doing it, even though I've already got the automatic anti-lock brakes. I caught myself doing it anyways. I was coming back from Busch Gardens, and we were looking up something on the road map, and I was on the interstate flying, as you might suspect, because the speed limit's like 65, 70 or something there, and I'm going about 70. And I look over in the map and realize, oh wow, there's Oxford, North Carolina. I didn't know that. And about that time, I look up and I'm coming up over a hill, and I'm on a little overpass over a road, and I've got about 50 feet in front of me before I run into a car going 0 while I'm going 70. So I hit the brakes. It immediately begins to skid. I let off the brakes and turn to the left a little bit to try to fit between the car and the railing of the over ramp. And I hit the brakes again. I begin to skid. I let off the brakes. I hit the brakes again. I begin to skid. I let off the brakes and come to a stop, 2 cars in front of that car. But literally somehow I managed to fit between the railing of the bridge and the car. And I look, and there's a car next to me, and they're like looking at me like, what the crap? So I will just tell you that pumping the brakes is what we are always taught to do, and I instinctively did do it, and you could feel in real time what was happening, because as soon as I was starting to skid, I would lose control, and it would try to, aim sort of off the side of the road, because the road has that bevel on it and stuff like that. But somehow I luckily did not crash and didn't kill any poor people. So anyways, now we're going to do figure out exactly how long of a skid mark would happen if we didn't have anti-lock brakes and we were going from 60 miles per hour to 0. So the net work is equal to the change in kinetic energy is what we're going to use. And in this case, the net work is going to be the friction force times the distance. And the change in kinetic energy actually is going to be the negative of the friction force times the distance, because the force for the brakes is going to be pushing this way while the car goes that way. So you get a negative work done. And that's going to be equal to 1/2 mv final squared minus v initial squared. But this part right here, of course, is 0 because we're coming to a stop. So I can substitute all this in. I'm going to say negative 0.205, and nobody really does 3 sig figs on this. I'm just doing it for numbers sake. And then, of course, times the normal force, which would be just m times g. So that's 2,250 kilograms times 9.80 meters per second every second. So this is just mu times the normal force. And of course, the normal force is just mg when you're on a horizontal road. So that's why I did all that. That's equal to 1/2 2,250 kilograms times negative 26.8 meters per second squared. Okay, the negative came because the 0 is in front of it. And 26.8, of course, is 60 miles per hour converted to meters per second. You can see that this actually is a problem that's independent of the mass of the vehicle. Really, all that matters is the coefficient of friction and your velocity. So what we want to know is what is D, which I conveniently left off when I wrote it for some reason. Okay, so now I'm going to say D is evidently going to be equal to 1/2 m v initial squared over, I'm just writing the formula out so we know in general what it is. So on a horizontal road, that's what we'd expect it to be, is mv initial squared over 2 mu s mg, which obviously the m's cancel out, be v initial squared over 2 mu s times g. And you can find that, in fact, in transportation engineering books online, as well as various tables the DOT gives people that are working in the field. When I actually do this math, I'm going to get 26.8 squared. Whoa. And I'm going to put a random 4 there. I'm going to divide by, now I'm going to use my parentheses, because if I don't, my calculator knows math better than I do. So it'll divide by 2, and then it'll multiply by mu s and g. So that's a pain. So 2 times 0.205 times 9.8. So that should be 178.76 meters. Obviously, we only use 3 sig figs at best, so really those are extra figures. So we do expect it to travel 178 meters. That's a good distance. That's bigger than almost 2 football fields, or it's probably comparable to 2 football fields. In fact, let me put it in feet. 179, if my 9 button ever works, meters, and I'll say 0 feet. Add those, I get 587 feet. So very close to 2 football fields, which would be 600 feet, of course. So that's about 587 feet. Obviously, you want to pay attention while driving at 60 miles per hour, because it's hard to fit 2 football fields in between you and the car in front of you, or the small child that ran out in front of you, or something like that. If you're in a school zone, we just had a terrible thing like that happen here in Currituck. A young lady was hit by someone in a 35-mile-per-hour school zone, hit at 70 miles per hour, and the poor girl died. I think she was 9 years old. It's terrible. Right in front of our high school, right here in Currituck. All right, now the next physics problem. That's so depressing. Anyways, the next physics problem is, we've sort of covered everything now that we could do regarding the work energy theorem, or all the different types of problems you can do with the work energy theorem. So there's really nothing left, which means I'm going to go ahead and start into chapter 8. So chapter 8 is actually on potential energy. It's actually on conservation of energy. So let's say chapter 8, conservation of energy. There I am with my M again. I always put like 2 humps on my M and 3 humps on my N for some reason. But anyways, conservation of energy. So there's 2 types of mechanical energy. And when I say mechanical energy, what I mean is the energy that we study in the field of mechanics. Okay. So in other words, in physics, not mechanics like, people that work on cars, but in the field of dynamics and mechanics of Newton. The types of energy are kinetic energy, which we've already seen. And generally speaking, unless you're talking about, as long as you're talking about point masses, then the kinetic energy, which can be written, as I told you before, Ke or K, is just equal to 1/2 mv squared. If you start to talk about a physical body that's more than a point particle, then it has the ability to rotate, and there's another type of kinetic energy associated with that. So you have an energy associated with its center of mass moving at some velocity, but you also have another kinetic energy associated with it rotating about its center of mass. And we'll discover that when we start to start to study rotational motion. This is the energy of motion. I'm so proud of myself for using the proper number of humps on my M. So this is the energy you have as a result of just moving. Okay. Now notice it does depend on your mass. It depends on your velocity. And for instance, I have a neat story about that. I was working on a master's in structural engineering at NC State, and I was had a series of injuries, shoulder injuries, knee injuries, stuff like that, but was still trying to maintain my exercise regimen. So I was out on the track running sprints and then running distances and stuff like that. And I went out to the track one day, really nice, beautiful day. I'm looking across campus because, the campus is really pretty and there's all sorts of pretty things to look at on campus. And I go to walk across the track to start on the inside lane, which is where I usually start. And I hear a bloom, bloom, bloom. And I don't think anything of it. And all of a sudden I get blindsided by this guy. And all I can see is just a second before he hits me, I look and I see this huge person. All I can think is, oh, this is my fault, man. I've screwed up. I'm going to hurt somebody because, I'm a big guy. So I instinctively grab and hold on to the poor fellow so that he won't be injured. Well, it happened to be a linebacker from the football team. You know, I'm pretty good size. I was 5'11". At that time, I was bench pressing about 380 pounds, 350, something like that. And I weighed about 220, 230. So, you know, I'm used to being kind of big to people, but this dude was like 6'5" and weighed about 300 pounds and had very small amount of fat, but it was kind of cute. You know, me like looking like a little ladybug hugging on to a cricket, all in my effort to protect him. And I said, "Oh man, I'm so sorry." I said, "It's okay." He was running sprints, and that, you know, literally just took off. And I walked in front of him, and he didn't even see me because he was just looking straight down. And I apologized. He said, "No, no, I should have been looking more closely too. I'm sorry." Said, "Oh, it's fine." And I walked off and began to urinate blood for several days. I found out I actually bruised my kidneys horribly. So that is the energy that you have as a result of motion. And you can see, because one, that guy was really heavy, so his mass was large, and two, he was running darn fast, so his velocity was large. Therefore, he had a buttload of kinetic energy, and that's what why we call it the energy of motion, because it's a result of many things. Obviously, it's a result of your mass and your velocity, but you only have it if you're in motion. The other one can actually cover a lot of different things, and that's called the potential energy. Now, this one is often used, called U. It's often called PE. It's also called V. And I think I've even seen it labeled T before. Okay, so there's a lot of different ways. I usually use U and PE. When we get to quantum mechanics, I'll use a V, but pretty much U and PE is what I use. And one case of it, so I said this covers a lot of different things. One case of it, for instance, is you can imagine potential energy is the energy you have the potential to deliver if the conditions are right. So if you take a spring and you compress it, and then, you know, have a little latch that holds it in place, that spring has the potential to do work. Remember, work is anything that can drive a nail, right? So you could imagine that spring, if it had a flat end on it, it could spring out and push a nail into a block of butter, say. So yeah, clearly that spring could be a potential energy. In that case, it's 1/2 kx squared, which we found before. Or it can also be, if you figure out how much work it takes to lift a mass m off the surface of the earth, then obviously from the free body diagram, we'd have F, the force you're lifting, pointing upward, and mg, the force downward, and you figure out how much work it takes to lift it to a height, say h, then you'd get work equals the integral of F dot dl. In this case, we really don't even have to do the integral because the force is a constant. You can see if I want to just apply enough force where it doesn't accelerate, then I'll have the summation of forces in the y direction equals mass times acceleration in the y direction, but the acceleration will be 0. Then I just get F minus mg equals 0. So F is in fact mg. So I get the integral of mg dot dy. Mg is in the j hat direction, and dy, I'm going to say I'm going upward, so I'm going to let the direction be indicated by the dl vector. And then the other one has to be from 0 to h, and clearly you get just mgh. So that's another form of potential energy. In fact, if you're going a distance h that's comparable, say, to the radius of the Earth, then you're going to get that formula we found earlier, which was Gmm over r. Okay, but as long as you're close to the Earth, you can just do this. So this potential energy can be a lot of different things. And then when we say conservation of energy, we could state it like this. We could say delta U plus delta K is equal to 0. And that works great. That's a version of conservation of energy. In fact, it's a version of conservation of energy that your textbook uses. I use a little different one because it can then be applied to all situations, including ones where we have dissipative forces. and including ones where you're putting work into the system and stuff like that. So my version, so this is not one you'll find labeled in the book, but it's certainly one I allow you to use and put on your equation sheet. My version, I don't use the deltas because I find that when you're dealing with certain potential energies, there's a sign in it that makes things funny. So that confuses my students. So what I do instead is I say U initial plus kinetic energy initial. And I usually use the KE just because it makes it a little more obvious. And then I say plus work in, that means whatever work you put into the system is equal to U final plus kinetic energy final plus work out. So maybe at the end of the problem, some kind of work is being done, plus E loss, where E loss is the energy loss, say to friction or heat or something like that. Now, when you use that equation, then you've got a term for everything, and there's not a definitive ruling on what work out is and what E loss is. The main thing is make sure you account for every way that energy is taken out of the system. And as long as you take it into account exactly one time, then everything will be right. You could even add a EN on this side. So you could add a EN, meaning the energy I put into it, if you wanted to. That's all I'm doing. I'm just trying to make a term for every type of energy I could get put into it. So the typical problem I do to explain this is really nice. And I always just make up numbers, and it makes this poor child dangerously going quite fast. So you imagine a child and her sled sitting on a hill, sitting on the top of a hill. Okay. And then her dad also is putting work into the system by giving her a push. Okay. Let's say her mass with the sled is 50.0 kilograms. And let's say the height here is H equal to 100 meters. I really should write 100 meters and then write equals H. Okay, so that's the height. And let's say also, so notice this force that he's going to push it with a force of 100.0 newtons, and he's going to push that for a distance D equals, and he's pushing parallel, so you just do force times distance. Let's say he pushes that for 2.0 meters. And then at the end of that, of course, she's got some speed, and then she slides down the hill, and that's going to give her more speed because her potential energy is going to go from mgh to just 0. So this side is H equals 0 right there. Okay. And what I would like to know is A, what's the V at the bottom? In other words, just before she hits this thing, because at the end of that thing, I'm going to have a spring loaded safety mechanism. That's going to keep her from being harmed by the high speed she might accrue by going down that hill. And I want to say, in fact, that spring constant is 10,000 newtons per meter. And I'll put a dot there so we know it's all 5 sig figs are correct. Okay, so part B, I want to know in part A how fast she's going just before she hits it. That's V at the bottom. And then part B is how much is the spring compressed. And what I will say is that will account for work out, is the spring being compressed. What I'm going to say for E loss is I'm going to imagine that there's a coefficient of kinetic friction equal to, let's say, 0.100, and that her equivalent normal force, so I'll write this like an average, is 0.85 mg. Okay, because notice up here it's going to be mg, and down here it's going to be mg, but along this it's going to vary because it's going to be mg cosine theta, mg cosine theta. So I've done some experiments, say, and I've ruled that the net effect is over this curve is about 0.85 of her weight is really what the normal force is. So let's do part A. We start at 12:30, so 1:45. Okay. So part A, I'm just going to fill in the stuff I know. The potential energy initially is going to be 50. I want to leave off the units times 9.80 times 100.0. That all gives me joules. The initial kinetic energy is 0 because I'm starting it the instant the father starts to push. And the work in is 100.0 times 2.00, which is, again, this comes out in joules, so I know everything works out right. So that's my work in term right there. Now my U final is going to be 0 because the height is 0 there, so mgh is 0. My kinetic energy is partly what I want to know, so that's 1/2 times 50.0 times v bottom squared. My work out is 0 for that part, but I do have an E loss for that part, and that E loss is, oh yeah, I need to specify that this distance all the way along here, all the way out to here, is in fact D prime equals 500.0 meters. So I'm going to take the friction force, which is 0.100 times 0.85 times 50 times 9.80 times the distance, which we said was 500. And that's my E loss term. So now I've showed you how to use the E loss, initial and final kinetic energy and work in. Part B will be related to work out because then I can just set the kinetic energy that I found earlier. I found the velocity. I can multiply that by itself and then multiply by 1/2 m and set that equal to work out, and that'll give me the same problem. So when I do all this math, I'm going to do I can do 50 times 9.8 times 100 plus 100 times 2. Now I'm going to subtract this junk over here. So I'll say minus 0.1 times 0.85 times 50 times 9.8 times 500. Now, hopefully I didn't overcompensate. I did not. So what I've got now is 28.375 times 10 to the third joules is equal to 25.0 times V bottom squared. So V bottom is going to equal, I'll divide this by 25. And we can see already this is going to be a horrible result for this poor child. I've got to take a square root of that. And lo and behold, I get 33.6 meters per second. Well, that's not as bad as it was yesterday. I had the 73 when I made up the problem earlier. So that's a little better. 33, remember 26 is 60 miles per hour. So this is another, what, 7 above that, which is about a fourth. So maybe that's 75 miles per hour. So on the order of 75 miles per hour. Yeah, that's bad for the poor girl, or poor child, I should say. But, you know, dads are sometimes dumb and make careless mistakes thinking that everything will work out just fine. Okay. Now, we could go and set up all this equation again.
One question.
Yes, go ahead.
What's that number right there on where it should be the on the right hand side where it should be the energy, the work net?
0.1 times 0.85 times 50 times 9.8 times 500.
So you're saying it's 0.1 times 0.85 times the mass times the gravity
Yeah,
times
and then times
500.
the length along the slope.
Wait, where'd you get the 0.1? Is that from the height?
That's the coefficient of friction.
Oh, okay, that's right.
Yeah, and the 0.85 is from how we're estimating the effect of the hill's angle changing. Now for part B, we could go ahead and write all this equation again, but we really don't need to. What we've seen is that all of the energy has basically been converted to E loss plus kinetic energy final. And the kinetic energy final, obviously there's going to be a very small distance that this is going to push. And the friction force is so small compared to the spring force that we can ignore any E loss due to friction on this, at least in the first order approximation. So what I'm going to do is just take that kinetic energy, which is at the bottom, the kinetic energy, and set that equal to work out. So I'm going to say 1/2 times 50.0 times 33.69 squared is equal to 1/2 of 10,000 times x squared, and solve for x. And when I do that, I'm going to get, let's see, 0.5 times 50 times answer squared. That gives me 28.375 times 10 to the third. That's the, that's also what we got after the subtraction. And then what I'm going to do is divide that by, or multiply by 2. So I'll say times 2. And then I'm going to divide by 10,000. Now all I've got is x squared. So now I got to take the square root of that. So I'm taking the square root of the answer. So notice that's what I did. I did 0.5 times 50 times 33.69. That gave me the kinetic energy. And then I took the kinetic energy, multiplied it by 2, and then divided it by 10,000. Now I'm going to take the square root of that, and I'll get 2.38 meters. So the girl is going to compress the spring 2.382 meters. So, a good 7 feet or so. And I like that example. I do essentially the same example every semester, whether I'm in 201 or 241. Basically, I just make up a problem where someone's on a hill, and that shows you how to use each of the terms. Now, I could have actually said the work out was work done against friction, and I would have put the 0.1 times 50 times 0.85 times 9.8 times 500 there, and then I could have put the E loss as the 1/2 kx squared. That was fine. The main thing is you just want to make sure you account for every type of energy exactly once. If you do it more than once, then you're obviously making a mistake. But that's the way you can use this equation. I think it's much more powerful looking at this because it takes into account that energy is not always conserved. Now, what we got left for chapter 8 is some details about the beautiful mathematics of conservative forces. So the forces that can be applied such that you use this nice little version or this version without these are called conservative forces. And there's a mathematical test that you can do to determine whether a force is conservative or not. And it turns out to be a cool little thing from calculus called basically it's called a curl, which is not only a cross product, but it's a cross product with a partial derivative vector operator. So it's some cool stuff like that. But it turns out if one of those facts are true, like the curl of the force is 0, then you automatically get these other things that come from it. Okay. So for instance, the curl being 0 tells you that there exists a potential that's a scalar that can be used to sort of represent the motion. That's why we have a potential energy. That potential, in fact, integrated from A to B to calculate how much work is done in going from A to B is independent of the path chosen. So you can go all along the x-axis and then shoot up, or you can go diagonally there, or you can go all along the y-axis and then shoot over, or any other path, and it doesn't matter. And another equivalent thing is that you can calculate the work done in a closed circle, and the change in potential energy would be 0. And another thing you can do is it turns out that that's the result of a exact differential equation. So if you've had differential equations when you had that m of xy times dx plus n of xy times dy equals 0, that's what I mean by that type of equation. So all of that stuff comes together, and we'll show you that. I'm not going to make you do much with it because it's pretty complex math, but it's a neat fact that can help you, and it's really going to help you when we get to electricity and magnetism in the second semester. So any questions on that?
Any question? Is there any chapter 8 homework due this week?
No, it won't be
Okay.
until the following week, because I still got some more of that to do. So it should be due. I think the concepts will be due a week from Sunday, and then the problems will be due Wednesday thereafter.
Okay, thank you.
Okay, I'd start on it anyways, just so you don't lose your edge. Just do a couple of them or something. But other than that, you're free to go, everybody. I will wait
Wait,
around.
when did you say the homework was gonna be due? Because on the
On the mastering it, yeah, I didn't know I was going to start the 8 yet. That's why I haven't necessarily said it, but my intent is to set it to a week from Sunday for chapter 8.
this Sunday, so a week from this Sunday.
Yeah, so that'd be
Okay.
8, 9, 10, that should be the 17th. And that's just the concept ones. The other ones will be on the 19th, which is Wednesday, or the 20th, whatever Wednesday is.
All right, thank you.
No problem.
Wait, so chapter 8, good. Chapter 8 is the only homework that we have to kind of be working on right now.
If you've done chapter 7, then yeah, but chapter 7 is still in play. Or actually, I think chapter 7, yeah, chapter 7 should be due Wednesday. So you should make sure you get that done. And if I remember correctly, I think the practice test is on chapters 1 through 7. No,
Yes, sir.
it is 1 through 8. That's it. Sorry.
So chapter 7 and starting chapter 8 is kind of the homework
Yes.
to be working. Okay, cool. Thank you.
No problem.
And it's also the same day as the midterm, right?
Yep.
Okay.
Yeah, so that's why I definitely want you to get some of chapter 8 done. Partly because you've covered a little bit and we'll have finished it by then.
What
Wait,
which
so-
chapters? Sorry.
I think you had the same question. Which
Which
chapter?
chapters? Let me look up that to make sure. I'm looking at D01C, and I'm looking at the practice midterm. Yeah, it's 1 to 8 is what the midterm's on, and the practice is up. Let me double check real quick. I think I'm gonna put it up right now.
If you're putting that up right now, chapter 7, I don't see it listed. I mean, I could go on to the my
I haven't had time to put it in this module yet, but it's definitely there. It's definitely in the mastering side, but I'll try to put that in today too. That's just something I just started doing this semester because it used to not work. So it's been haphazard whether I get it done or not. But the practice midterm for midterm is up now. The one that you can take a bunch of times is up. The one that you are only allowed to take once is won't be up for a little while, but sometime today though.
Okay, and just so I'm clear, so we're gonna finish chapter 8, and the chapter 8 will be pretty much due that following Sunday. So, the midterm is gonna be like
Next
next week.
week.
It's gonna be the week after.
Yeah, the midterm's going to
Or
include
is it gonna be
chapter 8,
that
but the
Thursday?
homework won't be due until after it.
Okay.
But I think you'll get plenty of practice if you do a couple of the problems and just do the practice test. You'll get plenty of practice and time.
Okay.
Woo.
Sorry about that.
All right.
No problem. Does that answer your question as well? I forgot who it was now. Was it Tristan? No, it wasn't Tristan. All right. So yeah, the practice test open. Oh,
All right.
All
Have a good day, Professor. Good
right.
weekend.
You too. Take care.
I had a problem like with the camera quality. Like I can't actually like understand, like I can't follow the lectures.
Yeah, that's an ongoing problem. I try to explicitly say what I'm doing so you could in principle write it down. I've even put it on the Ethernet cable, so I'm not using Wi-Fi anymore. I don't know what I can do other than that, but I do put the videos up immediately or as soon as I can after class, and the notes are up as well. So,
'Cause- Oh, wait, where are the notes? Because I could only find the videos, and like the videos had just as bad camera quality. So
yeah,
it's like,
if you look at the modules, there's a module called Important Documents and Links. And
Okay.
I give you a link to my Google Docs there. And not only
Alright.
that, you've got 2 other classes that usually come up before yours. So even if you didn't want to or didn't have your class yet, you could still use their notes because they're usually covering the same thing and they happened
Okay.
before you. So you're a little bit more fortunate because you're the last 241 class of the week.
all right, thank you.
No problem. Anybody else? Mark, do you have any questions? All right, I will see you guys later then.